the first quadrant, but then it puts it right at 0. And so as I do, I always like to see the origin. Most of you are, I give you the window and you're pretty happy with it. Sometimes we make some changes. So what we have, it's from 1 to 3, so I'll make it 1 to 4. Scale by 1. And -1 to, I'll make it 7, scale by 1. So between 1 and 3, I've got infinitely many. And what I'm looking at is an output value of 16/3, which is 5.333. So if I put a point on this curve, I'm then looking for where on this curve, what's the input that would give that to me, and how do I know where to place that point? Well, I'm going to place it where I have just found my average output to be. So I'm going to place a point on the curve. Now, with the Inspire, you don't always have to change the input. What you're really wanting to do is change the output, because you know that output has to be how much? 16/3. So I'm going to make sure that my calculations were correct. I'm going to put 16/3 as my output. So we can either change the input or the output, and it goes to 1.73. Anyone know what the square root of 3 is? Approximately 1.73. Okay. Okay. Yeah, I keep saying that not all of the integration problems are based on area under a curve. We've got a lot of problems that use derivatives. And we looked at some of those applications in section 4.7, for instance, the optimization one. And in, I'm losing the number of it, but the one with the related rates one, back in chapter 3. So if we are looking for other problems, we need to realize that we can use things other than area under a curve. So let's see what we've got here. The volume, V in liters of air, in the lungs during a 5-second respiratory cycle is approximated by this model. Who created this model? You did? Me? No. Someone who has analyzed the data, who has taken the data and has looked at a scatter plot and has decided what function would best approximate that. And so they're using a cubic curve that has a negative coefficient, so it's going to go from second to fourth instead of the usual third to first quadrants. Okay, so this is giving us the liters of air. So if you're thinking about your own lungs here, in a 5-second respiratory cycle, this is approximating the volume of the liters you have in your lungs, where T is the time in seconds. Approximate the average volume of air in the lungs during one cycle. So if 5 seconds, we're breathing in and out. So of course the volume of air is changing as we breathe in 5 seconds. How many different liters, how many different volumes do we have in 5 seconds? Infinitely many. Okay. What is the average volume of air you have in your lungs in any 5-second interval? That's what the problem's asking. Now I can see where this could be important if you're in the medical field. Anyone here in pharmacy? Okay, can you relate to something like this? Do you talk about anatomy and drugs reaction to, not yet, but you will. Pardon? Oh, no. Okay. But, you know, you can imagine if you're a medical field, you need to know what the reaction of a drug might be, what is the maximum or the minimum amount of lung capacity that a patient must have. And, of course, there's lots of other factors that might enter in. But, you know, you need to know what's the average. You need to know, you know, maybe you need to know the maximum in, but we're going for the average here. So this is what the problem is doing. So you've got this problem. How you solve it? Because you can't take infinitely many outputs here and then divide by. And by the way, what's the interval we're talking about? Yeah, 0 to 5. Okay. So we can't look at infinitely many and then divide by 5, but we can use our formula. So the average volume of air can be found by 1 divided by 5 minus 0, integrating from 0 to 5 on what? Going to be that, okay? So instead of writing all of that out, this is right up there, I'm going to just say V of t dt. We often kind of forget unless we are reminded that that has to be there. Okay. So we've got 1/5. And that's pretty simple. That's just, again, we're in pre-5.5, so we don't have to work too hard on getting this derivative. But we have 0.1729 t squared divided by 2. Plus 0.1522 t cubed divided by 3 minus 0.0374 t to the 4th divided by 4. I can't read my own writing, so I'm going to, there we go. Okay. Integrating from 0 to 5. Now, if you look at this, kind of an easy problem, right? For one of those boundaries. Put 0 in, you got 0. Okay? So we don't have to worry about that one. So we just have to put the 5 in, actually. So we have 1/5. And again, we are thinking of this antiderivative of 5 minus antiderivative of 0. But if we put the 0 in, it will just be 0. So it will be a little easier here. And this is one of those problems where, you know, aren't you glad you got a technology piece? Imagine what I had to go through. You guys should just really feel sorry for people like me who had to struggle so hard. We didn't have, you know what though, we didn't have problems like this either. We were not allowed to look at these that had actual numbers in them. They were all just pretty numbers, which left us to think, so what? Life doesn't hand us all those pretty numbers all the time. Okay, so again, this would be then minus 0. You know, get your calculators out, your Inspires, put them on calculator page. Now, if you wanted to, you could do the whole thing in one keystroke, meaning in one line on the Inspire. And that's what I would do to check this. Okay, I would just put this in and check it. But if you do it by hand, you know that your analytical work is correct. And when you do this, because you got decimals, you're going to get an approximated answer. So I'm waiting for an approximated answer, hoping that it matches what I have here. Brendan, do you have an answer yet? Yeah, I like that answer. Now, this is an actual problem, so we've got to put some units on it. What would you put? See, there again, you want, yeah, well, I guess you would. Let's see, volume would be in liters, though. Okay, so we would just have to say liters on that. So this person, probably based on age and height and maybe weight, but this person in 5 seconds has an average amount of air in their lungs of about a half a liter on the average. Doesn't mean that they always have a half a liter, but on an average, over the 5 seconds, it goes up, it goes down, but on an average, they have half a liter. Yeah?
After we buy